everybody, and welcome to Classical Stuff You Should Know. We are a podcast about, the world of learning.
Oh, man.
And specifically, older learning.
None of that newfangled learning.
None of that newfangled learning, which everyone else is doing. We're doing the old stuff. And we're trying to bring the classical world to you in fun and digestible ways. My name is AJ Hannenberg, and I am joined by Mr. Thomas Magby.
Hello.
And Graham Donaldson.
Hi.
And today we're answering the question, what is a postulate? And you probably shouldn't ask bees, and you shouldn't axio me.
Oh, my
But
word.
you should axiogram.
Oh, my word.
Yeah, I nailed that one.
I'm going to be an apostate from this podcast. Kind of.
Can we excommunicate?
I don't know. Who's the Pope of the podcast?
It's obviously Graham.
Oh, sweet.
I think you're the Pope.
Oh, okay.
Graham is the Pope.
First among equals, boys.
I'm the bank that funds you because I pull all the strings in the background.
That's true. What's Megby?
I could cut off the resources to the podcast.
That's true.
I'm the one with the bank account.
That's true.
What do you mean?
Yes, but I'm the one, I can shut down all operations by just not editing and entering the episodes.
Oh, fair point.
I post all of our videos. What's that worth?
Oh, man. As Pope, I don't like this kind of talk.
Too much division.
I'm in charge.
No, today what we're going to be talking about is a lecture given by a mathematician by the name of Jacob Bronowski.
Wait, that whole book is one lecture?
Well, it was, so what this is it is a series of lectures. They're called the Silliman lectures, which are lectures that are given at Yale. Actually, let me read it's the Mrs. Hespa Eli Silliman Memorial Lectures.
Oh, why didn't you say so? I've never heard of
Oh,
it.
Yeah.
okay. I thought it was with a thing.
Strikes a chord.
Yeah.
So it is a series of lectures given to the Silliman Foundation. So let me read the little lecture preamble thing, whatever they want to call it. On the foundation established in memory of Mrs. Hespa Eli Silliman, the president and fellows of Yale University present an annual course of lectures designed to illustrate the presence and providence of God as manifested in the natural and moral world. It was the belief of the testator that which is a word I never knew, that any orderly presentation of the facts of nature or history contributed to this end more effectively than dogmatic or polemical theology, which should therefore be excluded from the scope of the lectures. So only like natural theology or history. Let me read that again. The facts of nature or history contributed to this end, the presence and providence of God as manifested in the natural world, more effectively than dogmatic or polemical theology. The subjects are selected rather from the domains of natural science and history, given special prominence to astronomy, chemistry, geology, and anatomy. The present work constitutes the 44th volume published on this foundation. So I don't know if the Silliman lectures still go on, but they're essentially talk about God, but don't use theological postulates. Give special preference to astronomy, chemistry, geology, and anatomy.
They went through 2019.
Oh,
and then there was no lecture 2019, 2020. I assume COVID, and then Wikipedia has not been updated since then.
Interesting. Yeah. So the very nature of these lectures are, this is going to be interesting as the episode goes on, but are very much born out of an Enlightenment belief about using science and nature to talk about everything. So these lectures, the Silliman lectures were given for that reason. And Jacob Bronowski was a mathematician. He was Polish. He was Jewish, and left and escaped Europe from World War II. And also, and I won't hold this against him, but was a scholar on William Blake. He wrote a book on William Blake and really liked sort of Blake's metaphysics, or I don't know, Blake's crazy, drug-induced metaphysical poems. We done an episode on Blake. If you want to go listen,
you're not exaggerating. That's pretty much.
If you want to go listen to the wackiness of William Blake, go listen to our Blake episode, which we published on William Blake's birthday.
Yeah.
Completely and entirely on accident.
And got retweeted by the William Blake Foundation.
Yeah.
Even though it was a big roast of Blake.
It was a big roast of Blake. Anyway, but Jacob Bronowski, he wrote a bunch of these lectures, and a lot of them are very technical.
Did you look up so he's probably most well known for a documentary series.
I didn't know
It's
that.
called The Ascent of Man.
Oh, cool.
So it's kind of like a response to the Darwin Descent of Man. So it's from the 70s, so it's not like recent or anything.
Cool.
Anyway, and so in this selection of lectures that he gave, I'm going to be going through one of these lectures called "The Laws of Nature and the Nature of Laws." I don't know why he called it this, because this lecture doesn't really seem to have much to do with the idea of law. But anyway, "The Laws of Nature and the Nature of Laws," and in it, he talks, he sort of sets it up like this, that when we do science, when we talk about, like you go in geometry class and you sit down and you're going to be talking about a proof of triangles. Or if you're doing physics and you're given some sort of equation. So let's take gravity, the equation of gravity.
9.8 meters per second squared? You mean that?
Yeah, or the G is equal to, gravity is equal to some constant times, let's see.
The mass of two objects.
Yeah, the mass of two objects.
The distance, the square of the distance?
The square of the distance, exactly. So the example that I used was that the gravitational force between two masses is equal to a constant times the product of masses divided by the square of the distance. So that's G is equal to K m prime over r squared. That is the gravitational equation. Okay. Now, what he wanted...
It's so romantic.
Yeah, it's very romantic. Now, what he says is that when we are creating equations, they are essentially operating in similar ways as sentences. So let me just read you this first paragraph that he kicks off this lecture with. In my third lecture, so this is lecture number 4, I gave an account of science as a language which has been constructed in much the way that I have suggested all human languages have evolved. And I said that on decoding the cryptogram of nature, we arrive at a language of true sentences to which 3 kinds of entities contributed. So these are going to be important, these 3 entities. 1, as a result of decoding, we pick out inferred entities, or units or concepts for whose existence we have no direct evidence. Gravitation was one example I gave. So we don't have direct evidence of gravity, but we can infer it based on the things that we see. You drop a bowling ball on your foot, right? Gravitation was one of the examples I gave. Also mass, the electrons, inhibition. Those are the fundamental words which have been evolved in the language exactly as in any human language words for the objects and actions have evolved. The sentences are held together by a grammar, which tells us what kind of sentences we are allowed to put the unit into. The example that I used was that the gravitational force between 2 masses is equal to a constant times the product of the masses divided by the square of the distance. That is a sentence, G is equal to K m over r squared, that you are allowed to say. You are not allowed to say in the language the same sentence if you put r cubed at the bottom. That is the grammar. Okay, so he says that what you're doing in math is you have these inferred things, gravity, and then you are trying to put together those inferred things into sentences that make sense. You're putting together this equation, and that equation does a lot of work you can use it to talk about the nature of gravity. And that equation was brought about through experiment, through observation, and through proofs. And is that Newton? Did Newton come up with that one?
Gravity?
Yeah.
Sure. Remember an apple fall on his head?
Was he the one that sort of hammered out that equation?
Probably.
Yes.
Let's go with Newton.
Yes, that was Newton. That is the blind
Okay.
assertion bell.
Blind assertion bell. Newton invented gravity.
Developed the law of universal gravitation.
Awesome. So
Which
the law.
debuted in the book Mathematical Principles of Natural Philosophy.
Rock and roll.
1869. I have
So-
some more thoughts I'd like to share on that.
So he's saying. So the one way you can think about this is that such a equation is like a sentence in that we put into language. Okay. And then he says. Then I asked, are the things in the language real? Do the inferred units exist, like gravity? Does the electron exist? Let us take a really highly unlikely particle. Does the neutrino exist? And then, are the explanatory sentences true? Is the grammar true? Is Newton's formula a true sentence? Does it really say how masses act? I drew your attention to the fact that though it seemed to be true when it was written in 1666, it does not seem to be true in 1966 because other explanations had taken its place. How does this come about? So when we are coming up with an equation to talk about the relationship between masses and gravity, we are creating this sentence, which you can use into your proofs, and you can predict things, and you can use to make sense of the world. Every single word that we have is a metaphor. Words essentially are metaphors because they are stand-ins for things. So AJ, if I look at the blind assertion bell, the very word bell is, and like the noise that the air makes and that my tongue makes when I push the air out of my lungs to make the word bell, is a metaphor for that thing that is sitting on the table, right? All language is a metaphor that is making reference to an object.
Sure.
And so he is saying that when you do that with equations, and when you're doing that with something like, the equation of gravity, you are also creating a metaphor. This equation is a stand-in for this thing that we observe that's happening in nature. This is sort of a basic thing, but this is going to be important later on. So, there's another problem when we do this, though, that when we are talking about equations like this, and when we are running experiments to try to prove things, so you're going up and you're dropping the bowling ball, or you're trying to prove the relationship that masses have on gravity and whatnot, you as the experimenter are putting some sort of limitations around your experiment, and you're saying everything that happens in this box is relevant to my experiment, and everything that is happening outside of this box is irrelevant to the experiment. And in many cases, that seems to be a sort of a straightforward thing. But as he says, we have to decide. I said that is all due to the fact that none of our explanations can be true, that in some sense there is no ultimate truth accessible to us for the simple reason we have to make a cut in the universe in order to do the experiment at all. We have to decide what is relevant and what is irrelevant. Since I hold, and this is his view, since I hold that the universe is totally connected, that every fact has some influence on every other fact, then it follows that any cut you make at all is a convenient simplification. So when you are running, for example, a proof in physics and saying, I'm going to run this proof, or I'm going to try to prove this thing, or to use his language, I'm going to say this sentence about gravity, it's not arbitrary, but you are saying, it's a simplification, that in our science classroom, when we have our kids do their chemistry experiments, and they're sitting down in their chemistry lab and they're trying to come up with some sort of experiment to talk about, what happens when you bring fire to this compound. They have to set up their environment, and they have to do it in this way. But Bronowski is saying the humidity of the room, the effect of where Jupiter is in space, does have a bearing on the experiment, but we say we're going to have that's going to be irrelevant. We're going to count that as irrelevant. We're going to say that the things that are relevant are what's happening in our experiment, and everything else that's happening around us, the time of day, the humidity of the room, the location, the time of year, the height of the experiment is happening. That's going to be all irrelevant to what we're doing. That every single sentence that we say of nature is a simplification.
So was it in college that this guy took acid? Where did he come up with this everything is connected notion? I feel like it had to be a hippie trip at some point.
It sounds like a hippie trip, but I think what he's saying is
a Tool concert.
Everything is connected because, if you really want to get into a very basic rudimentary thing, everything is subject to time and space. So there's a connection there. Now, is the fact that things are connected in time and space going to have any bearing on our 10th grade chemistry experiment? Well, no.
Well,
but maybe.
I mean, this makes me think of the two-slit experiment.
Yes, exactly.
Right?
He's going to talk about that.
Is he really?
Yeah.
Oh, I'm so excited.
The light, the particle wave. Yeah. What's it called? The
two-slit experiment.
Who are the guys that did that?
Frederick II.
Michelson Morley, is that it?
Gerald Slit.
No. Michelson Morley. I think anyway. Well, he does talk about that.
That's awesome.
Yeah.
That experiment is crazy.
Okay.
Have we talked about that on air before?
Thomas Young, 1802.
Oh, maybe not. Maybe I'm thinking of something different. So every sentence that you say using science, so coming up with a metaphor for how the world works. So what Newton is doing, and what that law of universal gravitation did, was it created a framework for understanding the world, and for understanding basically all of nature, and that spawned sort of this great metaphor for the understanding of nature. And the sort of the great metaphor of the 17th century was the idea of the watch, right? That created nature was like a watch, and God sort of created this machine and hit play, and off it goes, right? And that metaphor was driving a belief about the world, that it was like a machine.
Computers did this also.
Yeah.
Just in how we think about how humans work, or like how memory works. Very much the development of computers and the kind of the different forms of memory in a computer often get analogized to humans as well.
Exactly. Like, let me just download some information for you. Or have you heard that?
Keep this in your RAM.
Yeah.
I was going to say short-term versus long-term memory, which is the RAM versus hard drive stuff.
Or the one that gets. Have you heard this in meetings at all? Anything where people talk about double clicking on something?
Sure.
Well, let's just double click on that.
Oh.
Have you heard that?
Yes.
No.
Oh,
It's gross.
it's where it's like, let's just really think about this for a second. So let's double click on this, AJ. Anyway, so yes, either technology drives our understanding of nature, or we create these metaphors for helping us understand stuff. This is why cosmology was, a really hotly debated thing in the later Middle Ages. Is the sun the center? Is the earth the center? Although I feel like we should do a classical stuff episode where we talk about how, the church didn't really hate Earth-centric cosmologies. They just didn't like Galileo.
Sun-centric.
Sorry, so they didn't really hate sun-centric, heliocentric universes. They just really thought that Galileo was a punk.
Yes.
But anyway, we can talk about that later. I lost my train of thought. What were we talking about?
Metaphors.
Yes. So when you are doing an experiment, or when you are saying a sentence of nature, you're coming up with a theory of universal gravitation, like what Newton did. It is essentially oversimplification. Not an oversimplification. It is a simplification. Now,
You're drawing lines in the sand.
if you're drawing lines in the sand, it is a very useful simplification. And as we're going to see by the end of this episode, it's probably the only thing that we can do in order to make sense of the natural world. But it is still a simplification. Jump in.
Even in your example of the gravitational equation, so just you said all these elements, but it was kind of quick. So the elements are mass of one object, mass of another. We can measure those. Distance between two, we can measure those. And then there's this magical term called the gravitational
constant. Yeah.
And that's basically we don't know what else is happening here, so just put that
in a constant.
And that is, you just kind of observe it and you just kind of average out and say, this is what the constant should be. When really what is going in there, what else is happening between these two objects that is creating this gravitational pull. Like that constant number is just kind of created for the purpose of summarizing this relationship.
Yes.
It's not actually, there's no thing called the gravitational constant.
Exactly. Yeah. So or it's also just maybe the grab bag, it's the average of all of the unknowns put into a number.
Exactly, right. And we just hope it's close enough to what's actually happening.
Yeah, and it's close enough that it makes this sentence useful.
Yes.
Yes, exactly. But then if you really start drilling down on what makes up that constant, well, you could get to the place where you actually blow up your metaphor, which is what happens with Einstein and the theory of relativity.
Because you get to Higgs boson and why does anything have mass?
Exactly.
And that's a whole different problem.
Good. So as Bronowski continues, so it is natural that your decoding cannot be right. And it is not surprising that while you keep on getting approximate good answers, the answers are better and better as you progress because you exclude less and less. It is in principle out of the question that we should ever have an ultimate explanation. That would involve setting up experiments in which the whole of the universe was perceived from a God's eye view. I do not think that there is a God's eye view of nature, that there is a truth, an accessible truth of this kind. The words that I used were that, while the universe is totally connected, we cannot extricate ourselves from our own finiteness. And, therefore, we do this decoding by a highly imaginative, creative piece of guesswork. But we finish with something which is only a gigantic metaphor for that part of the universe which we are decoding. So we're sorry, go ahead.
Do you think quantum computing will change this? Being able to simulate the whole universe all at once?
I don't even know if you can. Is that the promise of quantum computing?
Kind of.
I don't know. How can you simulate something that you were a part of?
Well, and simulate something in order to try to understand that thing. Like, you've got to program it in there somehow. So,
well, I think he would say that you can't. Even
Yeah.
that you get into this sort of problem of self-reference, which we'll get to in a second.
Okay.
Anyway, so he says yes, that if you are looking at a piece of the universe, gravity, you are creating sentences which you are saying G equals this thing, and that sentence is true, but it's also not fully complete, and you're not getting the God's eye picture. You are having to exclude things from that sentence because you can't have the entirety of the universe bird's eye view experiment on gravity.
Right.
So you were making this simplification, and then you were making this metaphor. What we're not going to be talking about in this episode, but something that we can maybe talk about in future episodes, which I find very fascinating, is kind of what Magby was already alluding to, is how metaphors then end up driving culture or driving our own beliefs about ourselves. What did man think about the universe when they thought that the earth was the center, or when they thought that the earth was the bottom, like in Dante? Or no, was it Dante? Where like
Same thing.
Yeah.
The center was the bottom.
Mm-hmm. What does man think of himself when the universe is like a clock? What does man think of himself when the universe is, and then whatever the metaphor we're living under now? Do we even have a metaphor we're living under now? It's
Cold, dark, dangerous chaos.
It's it's either that, it's cold, dark, dangerous chaos, or again, maybe the computer, the machine,
heading towards eventual heat death of the universe.
Yeah. So it's like a nihilism.
Yes.
Yeah, bummer.
A dead world, I guess. Yeah.
Mm-hmm. Okay, but then he gets to the point of this essay. And the point of this essay is to say that this is true not only in the realm of talking about like physics, the world of nature, but he says this is also true when you talk about it in pure mathematics. I have said all that again because that is what I've been working up to for 3 weeks. So this is, the fourth week of the lectures. And today I'm going to look at it in a more rigorous context, the context of theorems in mathematics. I'm going to be talking about math not as an abstract system, but as a formal language for extracting something from the universe. Okay, so if we go back to our starting point, we have inferred units, we have a grammar of explanation, and I'll define these things in a second. We have inferred units and the grammar of explanation that is called the axiomatic systems. Maybe we only have two things. I said there was three, but grammar and axiomatic systems are the same. So I think there's only two. So let's talk about this in regards to math. Now, mathematics very clearly exhibits this structure. That is, inferred units, for example, ideal points, which are not really points, and a grammar of explanation that is called the axiomatic system. This is where I get a little fuzzy on what he's talking about. So when he says inferred units, for example, ideal points, which are not really points, maybe I throw myself at your mercy as the resident math one.
I have no idea what that means. The thing that is coming to mind, and I don't know if this is what he means, is that take a simple equation, the equation of force. How do we calculate force? Force is mass times acceleration. Mass is, I'm going to get this wrong, so someone can make fun of me, but acceleration is in the units meters per second squared, right? That's, like I said, gravity is 9.8 meters per second squared. And then mass, I think, is measured in grams or kilograms. It doesn't really matter. Well, you multiply these together and you get kilogram meters per second squared, which is like, I just said that sentence. What does that sentence mean? What's a kilogram meter per second squared. What's that mean?
It means it's a really heavy yardstick that you've thrown across the room.
Yeah, I guess that's not far off, but it also has to weigh a kilogram, so it's a heavy yardstick. That you're throwing across the
heavy
room.
yardstick.
So then that's like a really messy unit. So instead we call them newtons, right? So a newton's not a thing, but also neither is a kilogram meter per second squared. So like in that sense, our equation is attempting to describe something, but we're creating. I mean, that's a made up unit.
Yeah.
There's no natural thing called a newton. I guess maybe is one way of saying it. I'm sure people disagree with that.
When we did our episode in Euclid had proofs, right?
Yes, but I don't know how. Again, I don't know where you're going with this. Eventually, he has proofs that pertain to Euclidean geometry.
Sure. No, I don't want to get too far afield. So when I think what he's getting at when he says there are inferred units, for example, ideal points, which are not really points, and a grammar of explanation that is called the axiomatic system. So when we do Euclidean proofs, he says things like, imagine a point.
Well, yes, but sorry, just because he mentioned, so Euclid starts with axioms. Euclid starts with, these are the things that are true, therefore I can start proving things.
Yes,
and then all of
exactly.
his proofs build on top of each other. But none of, this is from the episode forever ago, none of those proofs exist in reality.
Yes, exactly.
So again, as we've said, you've never seen a perfect triangle. You've never seen a 90-degree angle. You've seen an 89.999 degree angle, but never a 90 degree. But Euclid is still able to say things that are true about rectangles with 90 degrees, triangles with 180 degrees, on and on.
Because he has inferences and then he has axioms.
Well, everything, yeah, as long as his axioms are true, all of the proofs that follow are true.
Excellent. So then he's got the grammar, the axiomatic system, and then he's got the inferred units, so points,
I guess those would be points.
And the proofs that he makes.
I forget if points or lines, one of them is an axiom, I think, but I don't remember, honestly.
And this is where we get to, well, and then Bronowski continues and he says, okay, well, treating mathematics as if it was made up of inferred units, made up of concepts or inferred units held together by a grammar, so inferred units held together by a grammar is the basis of math that was invented by the mathematicians of Greece and Alexandria. He says this is sort of the foundation of math, that you have these axioms, and then from those axioms you can make these proofs and these inferences. But already Euclid knew that there was already problems with it, and this is where we get to the difference between axioms and postulates. So what is it? So Hannenberg, you teach logic. Do you remember? Do you talk about axioms and postulates in your logic class? Maybe not axioms.
My best guess is an axiom. I mean, isn't an axiom what we refer to in normal English as sort of like an aphorism? Or like it's a saying. Like a commonly accepted saying?
It's in math, it's usually given as like a given.
And then a postulate is something, it's a proposal, something that can be true or false that you need to prove.
Yes. That you need to prove.
Yeah.
That is not, yes.
It's not a given.
So, so for an instance, says Bronowski, in Euclid's day, there was already some doubt about what was called the postulate of parallels. It's also known as Playfair's axiom. And postulate of parallels is if you have a line and if you have a single point that is not on that line, there is only going to be one line that runs through that point that is going to be parallel to the other line. Is that the postulate?
Well, I think there are multiple ways of phrasing it.
Okay.
That's probably one of them. The other is that draw a line and put two lines through it that intersect that first line at right angles.
Oh, yeah.
If they intersect at right angles, they'll never
the postulate is that they will never cross.
Now, the way Euclid frames it is that he's saying if the inner angles are less than two right angles, necessarily they will intersect, but the opposite is that if they are right angles, they will never intersect.
Yeah. What if they're greater than right angles? Will they never intersect?
Intersect on the other side.
Oh, they'll intersect on the back end.
Yeah, you still have an inner angle that's less than two right angles.
Gotcha. So that is now. Why is that a postulate and not an axiom?
So this is what I was saying before. So what Euclid is describing, we now call Euclidean geometry because it describes a plane where that axiom is true. So this is hard to, this is verbal medium. But the thing so imagine a piece of paper. You can draw your three lines and make your two parallel lines on your piece of paper. Well, now fold that piece of paper so it looks like a cylinder. That parallel proof is no longer true because the line is following a curved surface, and the curved surface doesn't follow the same rules as a flat surface. So Euclid is true for Euclidean geometry. He's not true for non-Euclidean geometry. Anything involving geography, he's not correct for.
Good.
Because geography is not on a flat surface. The world is round. Hot take for the day.
Yeah.
Or like put it on a ball. If you
That's what I mean.
do a line, do two intersecting, it'll cross on both sides.
It'll cross on, yeah, exactly. Yeah.
Okay, good. So now so we're so
Or
even
not
in
cross, depending on
Euclidean's
Which way
even
it's pointing.
even in Euclid's time, he was sort of uncomfortable, or maybe even if Euclid wasn't uncomfortable, the Greeks were certainly bothered about the completeness of the consistency of axioms. Like they're still, it's like, okay, well we can put this on the plane, we can postulate that they're never going to cross, but we can't go as far as to say they're an axiom insofar as the plane is like eternal or whatever. But insofar, but to call it an axiom, it's only an axiom in the
limited scope
Yes.
of a flat plane. But as soon as you allow, you can draw a shape where you have a right angle at one point and then the line curves. So you technically meet the requirement Euclid lays out, but they are intersecting lines. That's what AJ is talking about, of drawing your lines on top of a ball. You can make them intersect even with 90-degree angles. So you're saying it's not an axiom because it's not always true. You can create a plane where Euclid's statement is not correct.
Well, I mean, I'm getting even maybe to the. We're working our way up to Kurt Godel, which is talking about the problem of formal consistent systems. But we'll get there in a second. So I guess maybe the big central question that this essay is talking about is, he quotes somebody named David Hilbert. I don't know who David Hilbert is, but David Hilbert was a contemporary of these guys, these mathematicians, including
Godel.
Including Godel and including Bertrand Russell. Bertrand Russell was really famous because he tried to basically like prove that math could be talked about as a real thing without using math. But basically what he ended up doing was just like having to create like a second math. and then like he had to create a third math after the second math, and by then everyone kind of got bored with Bertrand Russell, and then Bertrand Russell had a crisis where he realized he couldn't prove math using math, and then while this was happening, he like realized he didn't love his wife anymore. Anyway,
Sounds like a rough week.
Bertrand Russell was a rough dude. Anyway, but David Hilbert, who is a contemporary of these guys, sort of summarizes the quote, the question like this: "We really have to answer the following question. Is it or is it not the case that any sensible mathematical proposition that I can write down can or cannot be proved to be true from the mathematical axioms?"
Come again?
Let me write it again. We really have to answer the following question. Is it or is it not the case that any sensible mathematical proposition that I can write down can or cannot be proved to be true from the mathematical axioms?
So basically, do axioms work?
Do axioms work?
Yeah.
Yes. And do we use the like language of math to prove math?
Yeah.
Do we use like the axiom?
No.
Why not, Hannenberg?
Oh, I'm just making a blind assertion.
That's maybe all we can. That's probably.
Well, that doesn't, no, because with Euclid, you can make your assertions, and a chain of logic gets you from these are points to this is the area of a dodecagram or whatever. Like he gets to crazy places by the end. So doesn't that prove that as long as you're logically consistent, I guess is the problem that you need logic in addition to this thing called math? Like what's the problem?
Yeah, maybe that is the problem. Maybe that is the.
You need something outside of math to, I don't know.
Yes, that
Or that you need the box?
that you need to postulate, or you need to bring in something outside of the system to help make sense of the system. An outside axiom, the axiom of logic.
I guess I don't know what the system is in that case then.
Well, let me keep going, and we'll see if it makes any if it gets any clearer. Spoiler: I don't think it gets any clearer. Okay.
So we're following you down a path, but your lantern is going to run dry?
Oh, he's gonna run dry, and we're gonna be left in the dark, boys.
Sweet.
Where was I? Okay.
Can we use axioms to prove or not?
Yes. Suppose, so then let's move on with this. Let me give you a very simple example to that question about axioms, using axioms to prove things. Suppose I ask the question, is every positive number the sum of 4 or less squares? The answer to that question is yes, and I can prove it. Supposing I ask the question, is every even number the sum of 2 prime numbers? The answer to that question is that this was a hypothesis first made by Goldbach more than 200 years ago, and to this day, nobody knows whether it is true or false. Now, you might say, well, that is ridiculous. You just go on looking at every even number, and so you check the theorem. And he says, that's exactly what you do.
You can't do it, though.
You can't do it, though.
There are infinite numbers.
There's infinite numbers.
Keep going.
Yeah.
Turns
so
out.
there are some things that you can prove. Is every positive number the sum of 4 or less squares? And the answer is that yes, you can, and you can prove it. But then there are some that you can't prove because the only way you can prove it is by doing it by hand, and you can't prove it because it's infinite.
Isn't that the same problem? I'm trying to look it up. What's the 3x plus 1?
Yeah. That's the thing that infinitely regresses to 431 or whatever it is, or 421.
But there's no proof as to why.
It's a postulate. And maybe, do you want to explain that?
No, I mean, if I'm not I'm not going to get it right. It's that there's the equation 3x plus 1, and that can't be right, though, because how does it get smaller over time?
It's if you put a number in, and if that number is what is it? If that number is even, you divide by 2 and do it again. If that number is odd, you subtract 1 and then do it.
Okay.
I think that's it.
I'll try and look at
whatever.
it. It's basically that, but you get to a point where it's only looping over 3, 10. This leads to the sequence 3, 10, 5, 16, 4, 2, 1, 4, 2, 1, and
the 4, 2, 1 infinite.
And then, but the question is, why does it do that, basically?
And it's a postulate. Does it always do that?
And we can't know the answer.
And we can't know the answer to that. Hannenberg, you're looking confused. Maybe we'll talk more about that in the after.
Well, I'm fully tracked.
Oh, excellent. Sorry, I apologize. We'll talk about that maybe in the after show.
I'm merely bored because I've heard all of this before.
Gotcha.
No, I'm just kidding.
Okay, well, let's get up to...
I'm tracking, though. You're doing a good job.
Okay, thank you.
I'm with you.
This is again, I selected this essay because it's so outside my wheelhouse that I wanted to be someone who just wasn't railing against romanticism for
I'm thoroughly enjoying
every
this.
episode. Okay.
I'm not being facetious. I'm really having a good time.
Okay.
Are you going to read that book that's like in favor of romanticism?
What's it called?
I don't remember.
Oh, probably not.
Romeo and Juliet?
So, and then Bronowski says, all of math basically is trying to find shortcuts to answer those big postulates. Is there a way that you can prove that every even number is a sum of 2 prime numbers? Is there a way that you can prove that? Or can you prove the 2x plus 1, 3x plus 1, or whatever that equation is? Anyway,
the truth and the beauty is the truth and beauty is the book I was trying to remember.
Are there procedures to shortcuts? Okay. Turing tried to do this by doing his Turing machines, and then we get to this mathematician named Kurt Godel. And Kurt Godel published a paper called Part 1. And at this time...
What a title.
I know that at this time when Bronowski wrote it, Part 2 hadn't been published yet. And so he's like, I don't know if there's going to be a Part 2. I think there is a Part 2, but he wrote something called Part 1, where Godel proves that, and this is what he says Godel's conclusion was. And I tried looking into it, and it was I was punching above my weight class to really understand the details of Godel, but I think I can simplify it to its conclusions. But anyway, this is what Godel proved. Godel proved that if you have an axiomatic system of this sort, a formal system with formal symbols and formal rules of manipulation, there are 2 things wrong with it. 1, in the first place, if it is consistent, and that's a technical word, we'll talk about what a consistent system is. If it is consistent, then there are statements that it cannot prove. And not only are there statements that it cannot prove, but there are also true statements that it cannot prove. So this was Godel's conclusion of his very sort of awesome titled article called Part 1, which is that if you have an axiomatic formal system with grammar, with a formal system of grammar and formal rules of manipulation, then there are things that system itself cannot prove. But then there are also true things that an outsider can prove, but cannot prove using the formal system to do it. So let me give you a very simple example that I think fits into Godel's theory or Godel's proof. I don't know if it is proof.
Can we
Godel's
pause
thing.
really fast
Yes.
and note that part one is perhaps the best thing to title something if it's an intellectual paper, because it implies that
That's right.
there's more.
And if people are like, this is stupid, you can be like, well,
Wait for
just
part
you wait.
two.
Wait for part
and then
two.
if part one is highly lauded and
Yeah.
everyone thinks it's awesome, you just write down some vague notes and then die. And then it will be like, oh, if we only could have had the rest of his genius.
yeah, exactly. Yes, and then the people will be like,
It's the best possible
it's a great idea.
title. Okay,
Yeah, it's-
go ahead.
it's
I just
great
wanted
marketing.
to take a note.
So I think the problem of self-reference fits into Godel's the paradox of self-reference fits into Godel's problem here. If you took a note card and wrote on one side, the thing written on the other side of this note card is false, and then you flip the note card and you said the thing written on the other side of this note card is true, you've created a paradox, right? If you just use the note card can't do anything. Like it can't, like one side says it's false and then one side says it's true, but if it's, you screwed yourself.
But to figure out which one is right, you can't just observe the note card.
That's right. You can't just observe the note card. You can't know the note card itself cannot prove which side is true. But that's that sort of, you have that paradox. This is the kind of thing that Godel is talking about. And Godel is saying that whenever you have a formal system with formal rules like that, there are going to be things that are true that the formal system itself can't prove. Now, if the system is inconsistent, well, then you can prove whatever you want, right? Like you can say if 2 equals 1, well, here's a very funny story about inconsistent systems. Apparently, Bertrand Russell was at a dinner, and Russell was reputed at a dinner party to once have said, "Oh, it is useless talking about inconsistent things. From an inconstant proposition, you can prove anything you like." Well, it is very easy to show this by mathematical means. But as usual, Russell was much cleverer than this. Somebody at the dinner table said, "Oh, come on," he said. "Well, name an inconsistent proposition." And the man said, "Well, what shall we say? 2 equals 1? All right," said Russell. "What do you want me to prove?" The man said, "I want you to prove that you are the Pope." "Why," said Russell, "the Pope and I are 2, but 2 equals 1. Therefore, the Pope and I are 1. Right, so if you have an inconsistent system where 2 equals 1, you can, it's not a very useful thing. So, but if you have a consistent system, Godel's proof is that that system cannot use its own internal logic and consistency to prove itself, or that there are going to be true things that you can prove outside the system that the system itself cannot prove. And so if you feed it into the machine, it can't do it. And so then what you need to do is you sort of add axioms to it. And so you've almost got this like infinite regress of systems. So if you feed a new axiom into the machine to try and to complete a new formal system, you're going to run into Godel's problem with that formal system, and then you're going to have to put in a new axiom, and then you're going to run into that same problem that there's going to be true things that it can't prove. And you essentially get that frustrating situation that you get with like a 10-year-old who keeps asking you why. Well, why is the sky blue? Well, the sky blue is because of this. Well, why? Well, because of this and this and this. Well, why? And you eventually get to the place where it's like, well, your question of why, I can no longer answer you.
Because it's just the way it is, Sam.
It's just the way it is, kid. And so this is...
So Godel's saying that all questions lead back to it's just the way it is.
Or
yes.
some sort, like, because you can't use yourself to prove yourself, every system must appeal to something outside.
Yes.
In order for its veracity.
It's just weird because it seems like he's either arguing that these systems are too small. Like, essentially you need... I don't even understand.
To found it on a bigger system?
You need a system that describes all of
Yes.
the universe.
Exactly.
Which I guess would be pure math. Like, I don't even... But pure math... I was... Like, when physics is taught, it's you teach everything as if it's in a vacuum and there's no gravity.
Mm-hmm.
But, like, obviously that's not true. So I don't understand what it would mean to make a system that describes everything. You're not in math anymore, are you?
Well, I mean, especially because math is a metaphor. Is this, since these lectures are there to essentially prove godhood
Not
by
that
appealing
it's just
to
to prove
science?
God. I mean, it's just to be talking about God without just sort of postulating theological without revelation, like talking about God through science.
But because no system can prove itself, and every system must appeal to an outside something, eventually that has to, like, the buck has to stop somewhere.
Yes, the buck's got to stop somewhere, and
Can I say, sorry, the alternative is that you then only make systems that are very, very small.
yes,
So
like the note card.
like the note card, or in your gravity example, my gravitational formula is only for planets. It has nothing to do with two humans, one to another.
Yep.
So I don't know if Godel then takes it that next step or cares to, but it's just weird that what he's arguing seems to push two completely opposite directions.
It's that the reach of all formal systems is limited.
Okay.
When you Bronowski, here's a quote: when you axiomatize an arithmetical or mathematical system, you automatically impose a limit upon it. In a phrase that I have used earlier, you cut the universe in half. And so this is sort of even going back to our problem with experiments, right? You put some kind of boundary on the system, or you put some sort of boundary on the thing you're analyzing, and say everything outside of here is I'm not going to worry about it. I'm only going to worry about what I'm observing, and I'm going to be able to say something definitive about what I'm observing. But you can't. But if you go to the realm and say I've now discovered an axiom, well, you're wrong. You can't do that. Nature is not a gigantic formalizable system. In order to formalize it, we have to make some assumptions which cut out some parts. We then lose the total connectivity. And what we get is a superb metaphor, but it is not a system which can embrace the whole of nature. I'll continue on. We are really saying that there is no system of axioms which can embrace the whole of nature, or for that matter, the whole of mathematics. We therefore cannot attain the great wish that we have had ever since the day of Thomas Hobbes and Newton. We will never be able to exhibit the whole of physics one fine day as a gorgeous system with about 6 axioms and a few operations, and from that moment everything would fall into place. No formal system embraces all the questions that can be asked.
So is this kind of addressing the problem that we have with, microphysics and macrophysics? Like, things that happen on the micro level don't mirror things that happen on the macro level. The theory of everything that we've been trying to hit, and right now we have, I think the most recent postulate is string theory.
Even that I think is busted.
Really? String theory has gotten discarded?
I don't know the details, but like you have things that are true at different sizes, which I think is what you're saying. This is true in biology, that there's
in chemistry.
I don't know when he's writing, but like this
67 maybe?
Because current concept is around emergent properties of, again, I know this more for biology, I'm sure it's true for chemistry, but that things behave differently based on size. So then a thing that you can prove when it's at the atom level is not anything at the organ level or at the human level or anything.
Or if you go down you can predict how chemicals are going to react, but when you get to the level of like subatomic particles, there's no prediction. Everything is sort of random, which, that kind of blows my mind. You can have random motion, but then one level higher, you can have predictable motion.
Oh, quantum physics. That's what I was, not micro. It's quantum physics. Everything acts differently than there's quantum entanglement. There's like there's the strong nuclear force that we don't really know how it works. It just happens at a certain distance. Things stop repelling each other and decide they want to hang together. And string theory, I thought, was trying to sort of bring it all together into one picture, but maybe they failed. I don't know.
Let's go back to the paradox of the note card. Or this is also Epimenides, the Cretan. This is also the all Cretans are liars, says the Cretan. Right. This is that paradox as well. And when you use the phrase, the statement is, let's go back to the note card. So the statement on the other side of the note card is true. The statement on the other note card is false. At once, you said the statement is, puts you into a universe of discourse in which you are no longer using this language to describe things, but statements about things. And then when you do that, you can't get out of it. As soon as you add to them the statement is true, you're in trouble because you're bound to be landed into contradictions like the one which arises in the Epimenides paradox, that when Epimenides says all Cretans are liars and he himself is a Cretan, that language itself has a because language is only a metaphor, that when you are using it to try to make statements about true things, you get stuck in these paradoxes, which is frustrating because like the very basis of human consciousness is us using language to make reference to ourselves. And that is so the very fact that
I don't.
like our humanity depends on a consciousness which can be self-referential and also can assume that you also have that same thing going on inside of you. And so at some level, like you sort of take the consciousness of other people on faith, or I don't know.
Just to make sure I'm understanding, so I think you're referencing back your point at the very beginning about language as metaphor, and that in language we reference ourselves. But by that you mean Graham is a metaphor for the person that you are, correct? You don't mean that you are a metaphor. The words that we use to describe you are metaphors.
Well, if we really want to get woo-woo about it. No, I don't think so. But this does, I mean, as I was thinking about this, and maybe this is something we can take in the after episode as well, that this really does add a whole other level of interpretation to talking about Christ as the Word. That if we talk about like words and sentences, and if in the beginning was the Word, and I don't know, I haven't put enough thought into that to say something cogent about that. But there seems to be, like, when you think about it in this way, the idea of God being Word, there's something interesting there when you're talking about the like self-reference when it comes to language. I don't have a point there. It was just something that popped into my mind that requires, and that's something that Kern has talked about. Andrew Kern has talked about the relationship of God and Word.
I just think that some people then take that and say God is a metaphor, and so that is then a weakening of the concept of God, which I think
it's the other way around. It's that we're all the metaphor. Like, if God is the Word, then we're all the metaphors.
Because we derive all of our words from God.
Well, for me, this is...
all words get their wordness from God.
Yes.
Mm-hmm. But I still I like to think of the original Logos, right? Mm-hmm. And Logos was understood also to be like the foundational logic of the universe, right? It is how all things hold together. It is the reasoning. Mm-hmm. And so that seems more applicable to me, not just self-referential word usage, but saying that there is something all systems appeal to, and if he is the system of the universe, then he is the system all things appeal to, and isn't it funny that he is often paradoxical? So,
yeah.
Isn't it also funny that you two both are referencing the same thing? When you say word and you say logos, you mean the same thing. Mm-hmm. Logos is translated as word.
Yes.
But different metaphors are drawn out based on the way you use word, even just in different languages.
Yeah. To steal a line from Andrew Kern, when God speaks, there's no difference between word and things. Because when God creates, he speaks and then the thing is. But our words are signs. Our words are metaphors. When we speak, we don't create, but we kind of create. We kind of like sub-create by giving words to things. So when God...
put new clothes on them.
Yeah, when God spoke trees into existence, he spoke and then the tree existed. When we create the letters T-R-E-E and say tree, haven't made the actual thing, but we have sort of sub-created by giving the word as a sign to the thing.
We're derivative. We're all plagiarists.
Yes. Anyway, so I was going to say that we can go on and talk about, like, then therefore there is a high calling to be, when we're talking about rhetoric. If you're a teacher of rhetoric, that you are when you are teaching how to speak, it's not just for persuasion, but it is also as like a co-creator of truth. But anyway, that's not. Let's go back to Bronowski. So Bronowski ends by saying, therefore, that scientific method of doing experiments, and even when you get into the world of pure math, of talking about formal systems of axioms, it is never going to be or cannot be a solution to the problem of the universe, but a strategy. It is a methodology that is an approximation. You are getting closer to being able to say something true, but it is still, you're having to cut something out in order to say it. And in this essay, he makes the claim, and I'm not enough of a Godel scholar or enough of even somebody that it is a difficult thing to try to wrap your head around. But from what I understand, the Godel's solution that these formal systems can't prove things that are true, that you need axioms outside of it to prove things. That like somebody standing outside of the formal system can say, well, there's a truth here that the system itself, like put it in the machine's never going to figure it out, but I can figure it out. That seems to be, from what I understand, a troubling thought to a lot of people, and something that was pretty, not irrefutable, but has carried a lot of weight since when Godel published it. I'm not sure, but it would not surprise me if there are people out there listening to this podcast who are like
PhDs in math.
That are like, an amateur podcast on Godel. This is painful.
Tell them to send them
but send an email. See if you can answer it. But Bronowski's ends this by saying all we can do is use this method as a strategy. We can only use metaphors to try to understand and to give some sort of sense to the things that we can observe, like gravity. But that metaphor is eventually, I'll use his words. As soon as the system runs into a fault, into an inconsistency, the human mind, unlike the machine, has the ability to throw the whole thing away and start building up a new axiomatic system. This is the way general relativity has taken the place of the Newton system, and no doubt something else will take the place of general relativity. So if Newton's theory of general relativity was completely accurate, or was the machine, like it cannot, Newton's theory of general relativity, Newton's theory of not general relativity, Newton's theory of
universal gravitation.
Of universal gravitation, when it runs into a problem, and maybe the constant was the problem, or when it comes to some of to a problem, and that or the problem being that when things are in motion, they experience time differently. It can't deal with that problem, but we as human beings can, because we're outside of the axiomatic system, and we can say, well, screw that, and we can scrap the whole thing and create a new metaphor, whole cloth, to explain what we now observe. And I think the problem was that, yes, when you have things in motion, they experience time differently, and this is something that Newton didn't have the concept of when he posited his system. So we can scrap the whole thing, build a new system, and build our own new axiomatic system, and then we're going to let that thing run for a little bit, and then we're going to be like, well, crap, there's this other thing we now observe that isn't going to fit into the Einstein theory of general relativity. Now we got to scrap this whole system, and Bronowski is saying that is we're never going to get to the solution. We're never going to get the God's eye view of nature, but we are going to get better and better metaphors, I think, is what he's saying. Does that sound?
Yeah, they improve.
Sounds like it, yeah.
But they're still not
better.
They're still not 100% true.
Yeah.
By the way, I looked it up, and it looks like string theory is no longer our theory of the strong force. We have one, I think, called like QNC that includes gluons and...
There you go.
You're just making stuff up now.
No, I saw an article, and I did not vet the article at all. I have no idea where it was from, but...
Did you read the headline?
I did read the headline.
Proud of you.
Yeah.
So the conclusion of this essay is that maybe we can even talk about this in the after show, which is that when we are talking about science, or science gets thrown around as sort of the final arbiter of a lot of social problems. Well, science says you should do X, Y, or Z. It's a lot less clear. I mean, we're just working with metaphors. We're just trying to cobble together metaphors that make sense of the observations that we have. And every once in a while, we have these new observations and the advances in technology where we have to throw out those organizing principles and those organizing metaphors for something else. And it's a bit of a bummer that the only one we have right now is like cold, meaningless death of the universe.
Yeah, well, jury's still out on science. Yeah. That's what I hear.
Anyway,
science is a liar sometimes.
That's the takeaway from this episode.
I don't know if that's a classical thing that you should know, but if this is your jam, pick up Jacob Bronowski's lectures. Has been bound together into a book called The Origins of Knowledge and Imagination, and it's a delightful read. It's a complicated thing, and I don't even think I've done it justice with my sort of like trying to piece it together on the fly here. But
Is that picture on the front a guy sliding down a moonbeam?
no, it is a picture. It is a William Blake etching of a guy putting a ladder up to the moon in heaven, saying, "I want, I want."
Oh, sounds blasphemous. Cool. Well, this has been Classical Stuff You Should Know. Nice to end on a note of blasphemy.
It's William Blake.
Right.
You can find us all our stuff at classicalstuff.net. You can email at us at theguys@classicalstuff.net. We will try to answer, though we don't always get to every email. You can also find us on Patreon. It's patreon.com/classicalstuff. And you can tweet at us on the twits at CLSSCAL stuff. And I think that's it. That's it for us.
Cool.
So we will see you next week. And, metaphors and stuff.